Good afternoon. Great to be inside and not have to be outside. Probably it's better being inside at home, but that's a different story. So the last time we talked about real gases and how their behavior is different from the perfect gas or the ideal gas. And we have seen when we compress at a constant temperature, we compress a real gas, that we will come to a point where on the isotherm we suddenly have a flat line. That flat line looks like this. This is the isotherm. It's at one temperature. This is ideal behavior here, and suddenly we compress it and we have all this free volume. And what happened is the gas, which used to use a lot of space because these gas particles were flying around in that gas volume, suddenly condensed. So we had a phase transition from the gas phase into the liquid phase. And the liquid phase, of course, is much denser. When this happens, it leaves behind all this empty space. And so you can use that like a vacuum, essentially. You can use that empty space to push in the piston, and you get a volume decrease, but no change in pressure. And this is what this shows here, this curve. And this is what the difference between the ideal gas behavior, where you don't observe this, and then you have the real gas behavior. So real gases show phase changes. That's one thing. And there is a temperature, which is called the critical temperature. Above that critical temperature, any gas behaves like an ideal gas again. Above the critical temperature, any gas behaves like an ideal gas. So ideal gases behave at all temperatures like an ideal gas. Real gases have to have a higher temperature than an ideal gas to behave again as an ideal gas. So water at very high temperature would behave like an ideal gas. You need to have very, very high temperatures. And you see, this is the ideal behavior where P times V is a constant at a given temperature. This is called isotherms, and you remember that. And now, why did we have this deviation from the ideal behavior to the real behavior? There's two things that we have to consider. One is that the particles are having a volume. They're not just points, they have a volume. And that volume, of course, is limited. You can't get it smaller than that. So if you you measure a volume of a real gas, you have to subtract to get ideal behavior. This would be the ideal, describing the ideal volume. So this is the observed volume of a real gas. You have to subtract the number of molecules or that volume that the gas has. So you have to subtract that because it has a volume, a finite volume. Okay? With this, you get, again, ideal behavior. And then we talked about the intermolecular forces between atoms, and there were interaction forces, and these interaction forces are relatively weak forces. And I talked about dipole-dipole interactions and induced dipole interactions. So when I showed this with these tennis balls here, where when they have high kinetic energy, these interactions really don't play any role. That's why they behave ideal again, but these real gases. But if you have a lower temperature, then they slowly come towards each other, and these dipole-dipole interaction or induced dipole interaction suddenly play a role, and they stick together, and with this, you are decreasing the pressure. So if you want to come to the real pressure, this is the observed pressure, you have to add these molecules that show that interaction. So the pressure will be increased. So the observed pressure is lower than the ideal pressure. So you have these constants here, and I talked about this. And then we talked about phase diagrams. Phase diagrams depict changes of phase transitions, or phase changes for certain compounds. And of course, the easiest is we look at gases, and we could look at CO2, and CO2 wasn't at all a gas when I showed it to you. It was first a solid. It was a solid, and then I put that solid here on the table, and some of you could see some gas coming off, some steam. It went from the solid phase directly into the gaseous phase. So there was no liquid formed. And if you look at the phase diagram, this is the phase diagram of CO2. You look at this here. So the phase diagram, you have the pressure versus the temperature. And what we had the solid part here, the solid CO2, and we let it sit on the bench. And it warmed up. With this, the temperature increased. And suddenly we come to this phase line here that separates the solid from the gas phase. We come to this phase line, and we go into the gas phase. Not at all into the liquid phase. So that's the nice thing, or the very useful thing about CO2, that you can use it to cool food stuff without having a mess, the mess of water. If you use real ice, the ice melts, and then you have everything floating in water, which is not very nice. Anybody who went camping experienced this many times. The steaks were wet and all kinds of stuff, okay? So with CO2, you don't have that. And the reason is that CO2 can go easily at a certain temperature from its solid state into the gas state, and this happens around room temperature if you let it sit. Now, you also can go from the solid to the liquid by increasing the temperature. You have to have a higher pressure to go from the solid, that's the liquid area here, to liquid. So you would go from here to here. You also can, by the same temperature, if you have an isothermal compression, you increase the pressure and you go from the liquid phase to the solid phase. You can solidify it by increasing the pressure. And I showed this to you. We increased the pressure and we went from the gas to the solid phase. We went something like, from the gas to the liquid phase, we went here. Remember when we did that piston, that mercury piston, and first there was a gas, and then we increased the pressure at the same temperature, and it became a liquid, and then we released it, and it became a gas again. And so at the end, I showed to you, or Karen showed to you, the triple point of carbon dioxide. That was at this condition, at minus 56.6 degrees and 5.1 atmospheres. We had the solid, the liquid, and the gas coexisting next to each other in that tube that we have shown. It is a very difficult experiment. So I think that's where I stopped the last time. And I wanted to talk about water today. If you look, this is a positive slope here. This is the solid to the liquid line here, or liquid to solid. The slope is positive. Look at water here. The slope is negative. And that slope is negative, and this is extremely good for us that the slope is negative. Water is a very peculiar molecule in many aspects, but this is one of these peculiarities. So what you have is, if you have in the winter, you have solid water. What's solid water? Ice, okay? And you go to your favorite lake or pond, and you want to ice skate, all right? So that means the ice is on the top. It freezes from the top downwards, isn't that right? Okay. This is because this line doesn't go like this, but goes like this. So you have here the solid, and then you increase the pressure, and then you get liquid. What does it mean, increase the pressure? So if you go down in your pond, every 10 meter, remember from the diving experiment, every 10 meter, you increase the pressure by 1 atmosphere, or 10.3 meter exactly, 33 feet. You increase the pressure by 1 atmosphere. So at 20 meters, you have 2 atmospheres, 30, you have 3, and so on and so on. And with this, because you increase the pressure, what will the water become? Liquid. That is actually cool, because we would be really in big trouble if this would not be slanted to a negative slope. It would be slanted this way. Water would be useless for us, essentially, except drinking. But so you would have to start with evolution every year again, okay? Because the lakes would freeze from the bottom upwards if this wouldn't be like this. So that would be a long time till you could ice skate or ice fish or anything. And there would be no fish there because everything would be dead. And that's the nice thing. Because of that slope, the water becomes liquid again as you go down from the surface. Okay? That's one thing. And you can go, the water goes from the solid to the liquid and from the liquid to the gas. So you can, at certain conditions, you have a sublimation where you can go from the solid to the gas, but this is not the norm, essentially. So this would be the phenomenon that I just explained to you. And this curve is called the fusion curve here. That's the line depicting the boundary between the solid and the liquid, okay? When the liquid becomes solid or the solid becomes liquid. And then this would be the vaporization curve. That's the boundary between the liquid and the gas. The gas can vaporize, or vice versa, it can condense again. This would be the vaporization curve. And this would be then the sublimation curve, where you go from the solid subliming into the gas and vice versa. You jump a phase, essentially. That's called sublimation. We don't go from the solid to the liquid and to the gas. We go directly from the solid to the gas. So if you increase at this pressure, if you increase your temperature, you go from the solid to the gas, in this case. There's also a triple point of water, not so easy to be reached. It's around a tenth of a degree Celsius and 4.6 torr, and it's very difficult or nearly impossible to demonstrate this. So I haven't asked you that question, have I? No, obviously not. So we have here, this is the phase diagram of what? Why do you know that it's water? Because of that slope. That's the only phase diagram that has that slope, all right? Every other phase diagram has a positive slope in this here. That would go here this way. Water is the important part here, that slope. So now I have a process here. This is the critical temperature, okay? And what is above the critical temperature? Gases behave like ideal gases, all right? So what we do, we increase, we obviously are beyond this here, and this is an isotherm at this temperature here. An isotherm, we're increasing the pressure, okay? We're increasing the pressure from here to here. Would that be depicted by curve curve A, curve B, or curve C? Think about it, and then give me your answer. Don't forget Mr. Boyle. Can you hear me in the back there? Yeah? Good, thank you. Okay, there's a clear majority for this. 61% say it's B, and I agree with that. Why would that be? So we have above the critical temperature, how does the gas behave? Like an ideal gas. When we started out with gases at all, the first thing I was telling you, one of the first things was P times V is a constant. It's an isotherm. And this was Boyle's curve, wasn't it? The guy with the animal suffocations. P times V is a constant. Okay, this is this here. This would be, what kind of a gas would that be? A real gas. And this would be nonsense, okay? All right. So Good, you got it, but let's see those. But there's all there is to say. Above the critical temperature, the gas doesn't condense. It behaves like an ideal gas. Right there, there's not a condensation anymore. It's just everything is gas above here, okay? All here is gas, okay? And with this, the answer was B. And now we're going to come to a difficult subject, very difficult subject. Don't be too worried, but it's also difficult for me to get this across to you. We talk about thermodynamics, and thermos is a Greek word, and it means heat. And dynamics means power, heat power, okay? Now, it's not quite clear what that means to you, but we have talked about thermodynamics without knowing it in this class. We had some reactants, and these reactants had some kind of an energy, all right? And then they reacted with each other, and they released energy, and they were done here in a lower energy state, all right? This is essentially thermodynamics. We're describing the changes of heat for a system, or the changes of energy for a system. That's what thermodynamics does, and with this, we're going to dive right into it. All right, so, you know, the universe has a fixed amount of energy. After the Big Bang, the energy was fixed. Fixed amount of energy. Energy doesn't get created, energy doesn't get lost. So that's a very difficult thing to describe, because you really don't know how big that energy is. But you would know if you have a system here in a higher energy state, and the system then after it reacted in a lower energy state, you can calculate the difference in energy. That's what thermodynamics does, okay? So energy is essentially, the change of energy is the exchange of heat and work that the system can do. What does that mean? Okay? We see exchange of heat. That was exchange of heat. There was higher energy and lower energy, and there was heat then released. We can understand that, all right? Now let's see how we're going to define that. So heat and work are means to transfer energy between two systems, or within a system. So we have seen when we release heat in a chemical reaction, is that a negative value or a positive value? Negative. So that's our first definition. Let me get you the overview here before. We release heat, so Q is the heat, so it's negative, has a negative sign. If we put in heat in a system, this is our system. Let's say that's a gas, an ideal gas. The blue stuff is an ideal gas. It's in a sort of a piston, but there's no piston drawn at this point, okay? So this has a fixed energy here, and now I release heat. What would happen to that energy of that system here? The energy goes down, absolutely, because I haven't defined that there can be heat exchange here. So now I put in heat. What would be the sign? Positive, I put it. What happens to the energy of the system? Goes up, okay? Good. Delta E is larger than 0. Now, let's see, the system has a certain fixed amount of internal energy. That's what we were talking about. And now I have a piston, okay? And the gas could, for example, be compressed. So the outside pressure works on it. So work is done on the system. Is that okay? Work is done on the system. So let's see, work is done on the system. So the work is then done on the system, it's positive, okay? That's another definition. So now we can do work against an external pressure. Either we compress it or we expand it. Now, if the system does work against an external pressure, so I do that again, the system does work against an external pressure, what happens to the energy, internal energy of the system? It goes down, exactly. You're good. So, and what would be the sign of the work? Negative. If the system does work, so if you have an expansion against an outside pressure, then it's negative. So we have made our definition here, and we know that the exchange of energy, the change in energy is exchange of heat plus work, and this is how we defined it. If it goes in, it's positive. It comes out, it's negative. So now, energy is a state function, but heat and work are not a state function. So what is a state function? A state function only depends on its initial and final state. That was my initial state of the chemical reaction, and I did the reaction, and this was the final state. It was lower, it released heat. I don't care how I got there. I have the initial state and the final state. So what would be the heat sign when I have this condition? This is the initial state, this is the final state. Do I release heat? What's the sign? Now, I have this condition. Do I release heat, or do I need to put in heat to get up there? Okay, so the sign is positive. Now let me explain to you, if I have the camera on me, please, what a state function is. So I'm standing here, and I have a certain amount of energy. I'm going to go up here. Am I up there? Yeah, okay. I'm going to go up here, and now I have a higher potential energy. That was my initial state, that's the final state. The difference is the energy, okay? I could have done the following. Let's go back to the initial state. And I do this. Oh, whoops, I went wrong. Is it here? No, the final state is here. Okay. I go to the final state. What is my final state? I'm still here. And this was my initial state, that was the final state. I went up here and went down here. It doesn't matter. This is my initial state, this is the final state. That's a state function, all right? It only depends on the initial state and the final state. Let me explain you a little bit more about this, a little bit clearer. So we are here in Pimentel Hall, and I want to go to Denver. So I drive to the airport. So the initial state is Pimentel Hall, okay? I'm here at Pimentel Hall. I want to go to Denver, so I drive down to the Oakland airport, and I hop on a plane and go to Denver. Let's say I have a meeting at the Denver airport. So I started, my initial state was here. The final state was the Denver airport. That was one possibility. The other possibility, which I don't suggest, but would be also a possibility, I hop in my car, I drive down to Houston, and from Houston I go to New Orleans, and from New Orleans I go down to Key West, okay? And then from Key West I go to New York, and from New York I drive, in a long, long drive, I drive to Denver airport. Now I'm there where I wanted to be. So I wasted a lot of energy, but the initial and the final state is still the same. I started here, and I ended up in Denver. That's what thermodynamics is about. It's about state functions, okay? It's nothing to do with how you get there. All right, you know what a state function is, and heat and work are not state functions. They are, okay, they are means of transferring energy from one system to the other. So what we have really defined here, we have a system and we have the surroundings. So we calculate the changes of the system and calculated the changes of the surroundings, not the absolute energy, okay? So if you, for example, I ask, okay, one guy calculates the system, the change of the chemical reaction, and the other guy calculates the whole energy of the surroundings. That would be the whole universe. I highly recommend to say, I do system, okay? The system. You don't want to calculate the energy of the whole universe. You will be in very big trouble, essentially. So, and there is a conservation of energy. There is never energy created nor energy lost. If you transfer one thing out of a system, this system has lower energy, and the other system, the surroundings, has higher energy, okay? So this is the conservation of energy. We look at it as a system and the surroundings. Our universe, our thermodynamic universe, is the change in energy of the universe is zero. And it is made up of the change of the system and the change of the surroundings. And this should give zero, because we conserve energy. So we have set now the pace for this, and now we come to the real piston experiments. So if you have, for example, let's see, you have a you take a piston and you expand. You have this is a gas here, okay? This is the cylinder, and this piston can move up and down here, yeah, the red thing. You get it? Can move up and down. And on the outside, you have the external pressure, whatever that is, whatever we want to define it. There's a certain pressure. So now what is the work you do when you move that piston? Okay, you move it from here to here. The work is the force times the distance. Okay, the distance is the height as far you have pushed the piston up or down. And what is pressure? Pressure is force divided by a unit area. This is my unit area here. So now I put that force in here. I substitute that force here with pressure times A. So I have pressure times A. I have pressure, then it's the external pressure. A times delta H. What is A times delta H? A is an area, and delta H is a distance. With this, I have a volume. Okay? So the work is then minus the external pressure times, oh, yeah, here's A times delta H. I wrote it even here. Times delta V. It's the change in volume. You know now also that of a gas, and especially an ideal gas, the energy is directly dependent, proportional to the temperature. E is 3/2 nRT, all right? Or 1 mole, 3 E is 3/2 RT. So now, let's expand. Let's expand. So I expand from a certain volume to a higher volume. So I push against the outside pressure. So what would be the volume? The change in volume is larger than 0 because I expanded. What would be W? If this is larger than 0, what is W? W is smaller than 0, is minus, okay? Now the opposite case is I've compressed this now. I compress the gas, and the work on this here that I do, what is the work? So the change in volume, I decrease the volume from a larger volume. Wait, let's go back. From a larger volume to a smaller volume, the change is smaller than 0, okay? Now, if delta V is a negative number, smaller than 0, what's the work? The work is positive. Of course, you have to do work on the system. Remember, when we do work, plus if the system does work, negative. Now, what happened to the energy of that system here? I did work on it. What happened to the energy? Would the energy be the same, smaller, or decreased? I pushed it down. What happens to the energy? It goes up, doesn't it? Okay. If I expand it, now let's look at it this way. If I expand it, the system itself does work. So its internal energy goes down. And if I push on the system, then work is done on it, so its internal energy goes up. All right? So that hopefully you still follow me? About 20%. Okay, that's pretty good. Oh, no, more than that. So this is the gas. We have compression and expansion. So we looked at the work, and we also sort of deduced the internal energy, what happens to it. Okay, if the gas is totally isolated here. So the constant volume, you could do this at a constant volume. You would do this at a constant volume. That means you would have a bomb. It's not a bomb, that's what you think. It's a reaction bomb. You put your reaction in a big metal cylinder, which you screw it, close it, and then you let the reaction happen. So what happens? If it's exothermic, usually the pressure goes up. All right? That's why I call it a bomb calorimeter, or a bomb reaction vessel. So if you do by constant volume, the energy is E, okay? And E equals Q plus W. Now, can you do any work if it's a constant volume? No, only the work can be only mechanical. That means the piston can go up or down. But if you don't change the volume, do you do any work? No, you don't do any work. So work equals 0. So this is 0. With this, delta E equals Q. Okay, delta E equals Q, and I put a little V here to tell you this is at constant volume. It's just the heat that is exchanged. The change in energy is just the heat is exchanged. Okay, we didn't change the volume. With this, the change in energy is proportional to the change in temperature. That's what we always know about ideal gases. So, but our reactions that we do on the benchtop, are they constant volume reactions? Or are they constant pressure reactions? What's the pressure? Does the pressure change? Constant pressure. I do it on the benchtop, it's about 1 atmosphere always. We disregard the little weather changes, okay? It's 1 atmosphere. And so I say, a constant pressure reaction, I need a new state function. And the state function we call H, and we call it enthalpy. That's nothing but the energy at constant pressure. All right? So what would that be? The energy plus P times V, the pressure work. So what would that be here? Delta H, the change, would that be delta E times P times delta V plus V times delta P. Okay? But delta P is 0 because we don't change the pressure. With this, you have that expression. Delta H is delta E plus P times delta V. This is at constant pressure. And now, what can we do? So H is, we know this here is Q plus W, and this is the pressure work. That's minus W. With this delta H, it's just the heat that is exchanged. And this is what we want. Delta heat, H, the enthalpy, for example, of a reaction, is just the heat that is exchanged during that reaction. So that, and there you have a little P on the Q for the heat. That means that it's at constant pressure. Delta H is always at constant pressure, and that's the important part for us chemists here. And with this delta H, the change in energy at constant pressure is also proportional to the temperature again. Is that clear? All right? Nothing to it so far. Now let's do an isothermal expansion and compression. What means isothermal? Isothermal, it says it keeps the same temperature. So for example, I put heat into the system. This is my system. I put heat into it. So now, does the internal energy go up or down? Internal energy goes up. But now I say it should be isothermal. That means I'm not allowing the temperature to go up. So what would happen? It has to do something in order to leave the energy the same. So you put work. It does work. So work flows out of the system. So you put in isothermal, so this temperature should stay the same. You put heat in there, and you get work out of it. Sounds familiar to you? You've been driven here today? That's how your car engine works. That's how the steam engine works. And this is how thermodynamics came to perfection, because they wanted to optimize the performance of these steam engines. So what you do, the same amount of joules, in an ideal case, of course, the same amount of joules that you put in here, you come out, get out of work. Unfortunately, it's not like this because there are other factors in there, but for our consideration, that's what it is. Okay? So what would be the compression? What do I do? I do a compression. So I do work on the gas. I do work on the gas. I compress the gas. What happens to the internal energy? It goes up, isn't it? So I don't want it to go up. I want it to stay the same because I have isothermal conditions. If the energy goes up, the temperature must go up because it's 3/2 RT. I want to have isothermal conditions. Temperature has to stay the same. What can I do? I give off heat. Excuse me. It's so exciting, isn't it? I give off heat, okay? So I put in work, and you see, this if you put in work, that's positive, and you get out heat, that's negative. So you release heat, and with this the temperature stays constant. Isothermal condition, okay? So we can do this also. You put in work and get out heat. That would be the reverse of a steam engine. You make it steam by pushing at it. So now let me ask you a question. We have an ideal gas, and we compress this ideal gas. Okay? We compress this ideal gas, but we want to do this isothermally. Isothermally. What is the heat exchange? Is there no heat exchange? Is it smaller than 0, or is it larger than 0? Why don't you think about it and give me your answer? If you can answer this, you have understood everything I said so far. Just forget about all the formulas, okay? So you compress this. What happens to the internal energy of the gas? Okay, but you want to stay isothermal. I just talked about this. You want to stay isothermal. So what happens there? No. You did work on the gas. So compression is you do work on the gas, then not work can come out. No. What happens there? Isothermal. You have to keep the temperature the same. So you got to get rid of the heat. Okay, where does it go? Okay, let's display it. Yeah, that's pretty good. So there's 20, 32, 30, what is this, 26, 34%. Okay, so I'm explaining it for the 34%, which is actually I'm pretty happy with that. So we compress that baby here. Okay, we compress it. What happens to the internal energy? Goes up, okay? Now, but if the energy goes up, the temperature goes up. So E equals 3 half RT. So the temperature goes up. So what can I do that the temperature stays the same? I got to lose some heat, okay? I lose some heat, so I give off heat of the system. If I give off heat, is it smaller than 0 or larger than 0? It's an exothermic reaction. You give off heat. There it is, isothermal, delta E equals 0. W equals minus Q. The work is done on the system, and what will be then released is the work is minus the external pressure times delta V is larger than 0. If the work is larger than 0, what has to be Q? Q has to be negative, okay? You don't need to really think about this. Just think about how I explained it to you. Don't stick at this point with the equation. Just think about it pictorial, okay? So you push on that gas, the gas gets more energy, gets hotter. We don't want it to be hotter, so it has to lose the energy. Where would it lose the energy? It gives it to the surroundings, okay? All right, now comes the kicker here. Now we do the same thing. We expand against a vacuum. A vacuum, okay? What is Q now? We expand against the vacuum. What is Q? We isothermally expand against the vacuum. So if you would isothermally expand against the pressure, would the temperature of the gas go up or down? The energy would go down, okay? But do you expand against the pressure? You expand against the vacuum. Do you do any work? No. Got it. Huh? Oh, we need to discuss this a little bit. So that's the first vote, isn't it? Yeah. Okay. So if there is nothing there, if there's no pressure, and you expand against no pressure, what do you have to do? Work? No. Why don't you discuss this with each other, and then try to revise your answer? Some of you, at least. What did you vote? Hmm? If I do what? My home or? Yes! Excellent! You're getting it after the second attempt. But which is fine, okay? So you need to think in these ways that I try not to hang on too much to the formulas at this point. You will get caught up with the formulas. Okay, so we do an expansion, and the expansion is isothermal. That means the temperature has to stay the same, okay? So the delta E is 0, okay? Temperature has to stay the same. With this, the work is minus the heat exchange, or minus the heat exchange is the work. And with this, you don't do any work because you're expanding against a 0 pressure. This is your work. It's the external pressure times the change in volume. And this is 0. With this, the work is 0. And with this, Q is 0. And your answer has to be then B. All right. So let's make it even a little bit more complicated. We had the possibility of exchanging heat between the system and the surrounding. Now we don't allow it to exchange heat. We put it in a thermos and we said, we don't allow that gas to exchange heat. All right? But we can compress it and we can expand it. So, so if it doesn't exchange heat, which is Q is then 0, then as the change in energy is just the work. Okay? So if we do, the gas does work. The gas does work, and there is no heat flowing in and out. What happens to the energy of the gas? Goes down. Okay? So if, and our definition was, if the system does work, it's negative, remember, negative. So that must be smaller than 0. With this, the energy of that gas goes down, and this is also smaller than 0. Now you know so we don't let the heat flow in that we need to do the work. Okay? We have it isolated. Now comes the reverse. The reverse is we do a compression. Compression, we do work on the system. Work is positive. That means it's larger than 0. Again, isothermal Q is 0. With this, delta E is larger than 0, and that means the internal energy of that system increases. You press on it. That's how we started out, actually, with this picture. So let me ask you a question. We have here a compressed gas. Let's say this is carbon dioxide. Has nothing to do with the triple point or anything, okay? Has to do with what I just explained to you. And we have the compressed gas, and we expand it very quickly. What happens to the temperature of the gas? Does it increase? Does it stay the same, or does it decrease? Why don't you think about this and give me answers? So we're expanding a gas very quickly. So we expand it. What happens to the internal energy of that gas? And with this, does the temperature go up, go down, or stay the same? What was that? Adiabatic. Didn't I explain it here before? Let me go back a second. I'm going to stop this for a second. Let me stop this. Click everybody in here. Everybody click in quickly. Quickly, everybody. Everybody. Okay, everybody's there? Everybody clicked in? Okay. Wow, 242, that's good. So we stop it and I go back. No, we don't want to go this direction. We're going to go the opposite direction. Adiabatic means there is no exchange of heat possible. So I have it in a thermos here, and this is adiabatic. I think I said it, but I didn't use the word adiabatic. I said there's no exchange of heat possible. That's an adiabatic expansion or compression. So now we do this with the gas, and we do an adiabatic expansion against the constant temperature. That would be in this room, for example. We have a gas that expands in that room, and what happens to the temperature? Why don't you give me your answer? So you bought another minute for this. I appreciate your question. Thank you very much. That's important. If you don't get it, ask me. But I can't do all kinds of things, but a short question like this is perfect. That's Henry, huh? Okay, good. Yeah. Good, Henry. Thanks. Everybody's in, huh? Everybody, click in. I'm going to cut it short. I want to show a little demonstration. Done? Ooh. Okay, let me do a demonstration. We have here, if I could have the camera at the front, let me switch off the projectors here. So I have here carbon dioxide. Oh, I see it snow? Okay. What I'm going to do now, I'm going to spray this against this black cloth. What do you think this is? Exactly. It's not carbon dioxide. It became obviously so cold when it expanded that it froze out the air, the water in the air, and made ice. So that's how we do snow. Let me do that again. We're making all kinds of nice snow here. See that? This is how a snow machine works. You put in, thank you very much, Karen. You put in water, you expand it through a fine nozzle at very high pressure, and it cools off so much that you can make snow. All right? That's the same phenomenon. You make snow that way. You expand the gas at constant temperature. It happens so fast that the heat cannot exchange because I make this. So there's no heat exchange. Now there's heat exchange. You see that? Okay. So that's empty. Okay, that's empty. Isn't chemistry fun? Okay, let's see. Let me ask you that question now again, and please answer it right this time. We can put it line. Okay, thank you. So what does the temperature do? Let's make some snow, okay? There it snows, you see it? Give me the right answer. Everybody in? I need to finish up here. No, I have a minute still. Come on, there's 2 guys missing, 4 guys missing. All right, I can stop now? Yeah. I think everybody has that answer. I hope so. Yes. Okay. See you on Monday. Have a good weekend and a dry weekend.